Nowadays, we are surrounded by modern life with the development of technology. Electricity is one of the greatest technological innovations of mankind. Electricity production and growth have changed lives significantly, beginning with domestic use and industrial operations. Starting with our house, we use electricity for lighting, operating appliances, and most especially for all electronic devices such as cell phone and computers. Thus life become better. With the development of technology, it will be hard to envision a day without electricity. Moreover, a lifetime without it. According to the articles, more than 1.1 billion people in developing countries lack access to electricity, most specifically in rural areas. Without access to electricity, the prospect of development has been slowed.
Our team went to Porac, Pampanga to meet the local IT community. We were able to conduct a brief household interview to understand their lifestyle. The total number of family head is 117 and almost all of the households is made up of 5 people. Most of their job are construction worker, traders, and farm helper. As we have noted, their community has no sufficient supply of electricity. 2 street lights that lit up from 6 p.m. to 6 a.m. were given to them, but obviously not enough for all of them. Few households have car batteries and solar-powered flashlights in their house to light LED, and because of the darkness, some choose to sleep as early as 6 p.m. Some also owns a cell phone, which is essential during this time. Yet, without the proper supply of electricity, their choice is to go nearby barangay to get their phone charged, which will cost them a fee. A traditional 3-stone fire is their method of cooking. Just a few houses have gas stove that works on LPG. In the nearby mountains, they collect firewood to be used as fuel for cooking. Driven by the lifestyle of the Ata community, we, the researchers, came up with the idea of using waste heat recovery to produce amounts of electricity through the interviewed data obtained and comprehensive study that will mitigate the needs of the community with regard to electricity shortage. The study aims to develop a design of a device that will convert the heat produced from cooking into electrical energy.
First, develop a system design of an alternative energy source using thermoelectric device.
Second, gather TEC raw output data from actual testing using a data acquisition tool.
Third, utilize engineering knowledge to present a simulation of the booster circuit.
Fourth, prove that the system can charge a 6,800 mAh battery.
Fifth, present a stable output of 5 volts.
And lastly, prove that the system is capable of powering a 3 watts LED bulb for 10 hours through computation.
The extent of this study covers both actual and simulation part. For the actual part, the TEC 12706 is tested to gather actual outputs. As for the simulation part, the data gathered are fed into the booster circuit through simulation modeling. Lastly, the final output power is ready for consumption of either LED bulb or USB port.
There are 8 major components in the device, composed of heat source, heating coil, thermoelectric device, heat sink, boost converter, battery charging circuit, battery, and USB port. The heat source comes from 2 distinct cooking methods. First is a traditional 3-stone fire and the other one is a typical gas stove. The heating coil is made of copper and it is directly exposed to a source of heat. Functions as the heat conductor where the other end of the heating coil is directly linked to the thermoelectric device, the main feature of the device. Thermoelectric device, it converts heat energy to temperature difference into electrical power. For this specific project, the selected thermoelectric device model is TEC1 12706. This thermoelectric device fulfills the operating specifications of the device and it is readily available on the market. In order to reduce the heat on the thermoelectric device, heat sinks are used in this project design. A data acquisition tool will be used to gather the data required for the simulation section. This device is programmed to gather the sample of the data that will be evaluated during actual testing to assess the thermoelectric device outputs. Data obtained will be displayed automatically via an Excel file. Proceeding to the simulation part, there are two boost converter circuits will be simulated in the LT-SPICE software. One is for the battery charging and the other one is for output. Boost converter circuit is a DC to DC power converter that increases the voltage from its input source to its output, allowing the thermoelectric device to create a greater voltage that is necessary for the desired output of the study. The IC used in the circuit is LTC3119. For storing the electric output of the device, battery NCR18650B will be used. It has a built-in battery protection circuit in the design. For the output of the device, USB port is selected as it is widely used in electronic devices. This is very commonly used especially in smartphones chargers. For the external accessory, a LED bulb that has a built-in USB port will be applicable for this project. It is readily available and affordable on the market. Here is the full design of the prototype. It has a 3 detachable stands for the use of wood stoves. It can be removed quickly by just pulling off. Simply slide the stand into the specified slot when attaching it. For gas stove use, just remove the stand and place the device. The stove top has a diameter of 9 inch, which can fit into the regular gas stove size. The copper rod has 3 dedicated slots on the stove top, which can be removed if needed. There is a separate case for the circuit and the battery inside the main case. Between the cases, there is a heat insulator to lessen the heat transfer to the main case. The top cover of the cases is screwed for easy access inside. The first part of the project is accomplished through actual testing. The whole device is properly set up including the heat source and the computer to be used. The thermoelectric device is attached into the bent rod and duct tool sensor and probes. The duct tool is connected to the computer through its USB port to receive 5V supply. Once the fire is up, the thermoelectric device will automatically work and generate an output as a temperature difference between the hot side and the cold side is detected. The duct tool is used to detect, analyze, gather, and document the output of the thermoelectric device. Two DS18B20 thermal sensors probes are located on the top part of the duct tool. These DS18B20 sensors are used to detect the hot side and cold side temperature from the hot side of the thermoelectric device and heat sink respectively in degrees Celsius. The good thing about DS18B20 is that it can withstand temperature from negative 50 degrees to 125 degrees Celsius. Also, it is a waterproof thermal sensor. Another sensor named DHT11 is located on the lower part of the front of the device below the LCD to document the surrounding humidity and room temperature. On the top of the duct tool, a pair of wire which act as a probes can be found. These probes are connected to the modules that would read the voltage and current output of the thermoelectric device, namely ADS1115 and INA219 respectively. ADS1115 is a 16-bit ADC module with 4 multiplex input which is used for the voltage reading of the system. INA219 module is used for the DC current monitoring. Two SPST or single pole single throw relays are placed inside the duct tool device. These relays are used to break, trip, and shift the connection back and forth from the ADS1115 to INA219 module respectively. It then sends the signal to the Arduino MCU or microcontroller unit to convert the analog signal into digital signal for it to be transferable type of data using UART or Universal Asynchronous Receiver Transmitter protocol to the host computer. The DAC tool also has a built-in liquid crystal display. This LCD will display the status of the device whether it is sending data or not. Once the testing is done, the gathered data will be recorded via Excel spreadsheet. The Excel file will automatically generated and saved into the host computer. The saved file can be found automatically generated folder by the system on the same location of the Python file of the DAC tool. Lastly, as a way to make sure that the DAC tool is set up properly, a buzzer will provide 3 beeping sounds once it is connected successfully. Disconnect or has found an error in the connections.
Due to the COVID-19 pandemic, we were not able to fully complete the chassis. Hence, the new setup for the testing part was formed. As aspiring engineers, we rose above the challenge and adapted to the situation. We carefully strategized and planned how we can still arrive with our goal, which is to be able to somehow provide an alternative source of renewable energy for the less fortunate, or at least provide a feasible device when applied to actual production. The first and most important part of the testing phase is the setup itself. Select the heat source whether from a modern-day gas stove or by using 3-stone fire method. Next is the copper rod that will serve as the medium of heat transfer and is sandwiched between the erected stand and the pod. One side of the copper rod will be directly in contact with the fire, while the other end will be holding the thermoelectric device's hot side. On top of the thermoelectric device's cold side, a heatsink with thermal paste will provide aid in decreasing the temperature of the said side, thus increasing the thermal difference between the two sides. Since the chassis was not completed, the thermoelectric device and heatsink had to be strapped by metal wires in order for them not to wiggle or move. Next step is gathering the data. The thermoelectric device has 2 wires, positive and negative. These wires are where the data of the voltage and current can be taken from. The data acquisition tool has a positive and negative probe. These probes are connected to the positive and negative wires of the thermoelectric device. Aside from the probes that measure the voltage and current, the data acquisition tool is also equipped with 2 DS18B20 sensor probes. One probe is attached to the hot side and the other on the heatsink. These sensor probes will give the temperature reading of the 2 sides of the thermoelectric device. Another factor to consider is the temperature and humidity of the environment where testing is done. The data acquisition tool is also capable of gathering the environment's temperature and humidity through its DHT11 module. Once the setup is done correctly, the cooking process may now begin and the data acquisition as well. In the course of 1 full hour, the performance and other factors are closely monitored by the data acquisition tool. The data are sent from the data acquisition tool to the host computer. After the specified time, the data recorded are then stored in a Microsoft Excel file that is automatically generated. From the acquired data, the average value of voltage, current, cold and hot side temperature, environment temperature, and humidity are taken from each testing. This will provide the basis on how the thermoelectric device is performing. Once all the samples are averaged, we then proceed on computing yet another average value. This time, all the compiled average values are taken as samples. Aside from the final average value, in order to assess the performance better and to have a more solid basis, the standard deviation and lower and upper control limits are computed. These lower and upper control limits will further give an idea on what is the range of values that the thermoelectric device can provide. The following are examples of the graphs generated by the data acquisition tool. During the testing process, these graphs can be seen on the monitor of the computer. The user will have the opportunity to observe the behavior and the possible effects of the surroundings to the results drawn. The first 2 graphs are the last 20 samples obtained of the voltage and current reading. The third and fourth graph shows the temperature difference versus power generated and the voltage versus current characteristic curve of the thermoelectric device. Aside from the graphs, an Excel spreadsheet like this containing the data gathered for the whole testing process is generated for recording purposes.
The gathered data from the thermoelectric device will now be fed to the booster circuit to simulate and get an output of 4.2 volts, 1.6 ampere that will charge the battery. The configuration shown on the screen utilizes LTZ3119 or back boost DC to DC converter that will step up the input voltage to the desired output of 4.2 volts while drawing 1.6 ampere load current. To test the data gathered from the thermoelectric device, the researchers simulated a range of values starting from its lower control limit up to its upper control limit, including the average values for both stove and wood setup using LT-SPICE. The simulation runs for a 3 millisecond span of time. Here is the simulation for the stove setup feeding the booster circuit the computed lower control limit value of voltage and current. Take a look at the simulation results of the output values for voltage and current. We can see that the circuit was able to provide an approximately 4.2 volts and 1.6 ampere output, knowing that the value that was fed was the lowest possible value of the thermoelectric device. Now we're done simulating the lower control limit, let's try its upper limit. Notice that the highest possible input can provide an approximately of 4.2 volts and 1.6 ampere successfully. As for the average value, it is clear that this can also produce a value approximately of 4.2 volts and 1.6 ampere. Now, let's move to the generated values of food with the same circuit and same setup. The only difference is the source of heat. For the lower control limit, we use the values around 2.75 volts and 0.15 ampere as the input and still get an output of approximately 4.2 volts and 1.6 ampere. Simulating the upper control limit with the values around 4 volts and 0.22 ampere input, we still get an output of approximately 4.2 volts and 1.6 ampere. Lastly, simulating the average values for wood setup, we're still able to produce a value approximately of 4.2 volts and 1.6 ampere. Note that all the input values ranging from its LCL to UCL values is enough to trigger the booster circuit to produce a value of approximately 4.2 volts, 1.6 ampere. And these values are capable of charging a 3.7 volts lithium-ion battery. Another thing, each simulation result has a voltage spike in the first few microseconds of the simulation, but this would not damage the battery since the battery can handle this amount and it's within the safe range of its input voltage for a battery. The output of the boost converter, which is approximately 4.2 volts, will charge the battery. However, these values are not enough to charge the phone nor light a 3-watt LED bulb. In this case, we need another circuit simulation, a discharging circuit that will provide an output value of approximately 5 volts. The circuit shown on the screen utilizes the same IC, LTZ3119, with a different configuration drawing an approximately 5 volts and 600 milliampere output. We simulated input values ranging from 3.7 volts to 4.2 volts. These are the typical output of a battery. Notice that each simulation from 3.7, 3.8, 3.9, 4, 4.1, and 4.2 volts were successfully able to produce a usable 5 volts and 600 milliampere output. And these values are now capable of charging a phone or lighting a 3-watt LED bulb. The same thing goes here. A voltage spike during the simulation process appears. However, there is nothing to worry about since the voltage spike is tolerable and remains under 5.2 volts.
The battery protection circuit used for overcharging, overdischarging, and overcurrent. The circuit has DW01 where it monitors all the processes. The second IC, FS8205A, is an assembly of two field effect transistor. The operation of the FS8205A, the first field effect transistor, is the responsible for the discharge. The second monitors the charge. Positive wire is common. The first transistor controls the discharge process. If the battery voltage is below the critical voltage, which is about 2.7 volts to 3 volts, the signal from DW01 chip closes the first transistor and shutting down the battery from the load. The question arises, how can I recharge the battery if the transistor is closed? The fact that the DW01 chip is equipped with a system for detecting the charger, and if a charger is connected to the input, the IC will open the transistor. The second transistor responds for the battery charge. If the battery voltage reaches 4.2 volts, it closes. Get the charging time of the battery Panasonic NCR18650B. Use the formula on calculating the battery capacity. Battery capacity is equals to current times time in hours. Substitute the values to the formula and it will give you 6800 mAh is equals to 1.6 amp times time. Using the transposition property, it will give you the equation for time. Time is equals to 6800 mAh over 1.6 amp. The answer will be equals to 4.25. Convert it to time format and you will be finishing it to charge at around 4 hours and 15 minutes. To prove that the device can power a 3 watts LED for 10 hours use, the researchers computed the power consumption of the LED bulb. The formula is given as the current drawn of the LED times the usable time equals the battery capacity. We substitute the given 0.6 amps as the current drawn from LED times 10 hours for the usable time equals 6000 mAh. Since the capacity of the battery is 6800 mAh and the consumption of the 3 watts LED bulb is 6000 mAh, it can be concluded that even if the losses occur, the capacity of the battery is still enough to provide power to the bulb for 10 hours.
The testing results helped us in determining the proper configuration and circuit design for the boost converter and the discharging circuit. For the booster circuit, we have decided to take the output values of the lower control limit, upper control limit, and average of the performance of one thermoelectric device. The minimum input voltage value for the booster circuit is 2 volts to produce a decent value near approximately 4.2 volts while drawing a current of 1.6 amps. In line with this, we have decided to use 3 thermoelectric devices in series in order to make sure that if the device fails to perform on its average levels and produce values close to its lower control limit value, the booster circuit will still work and be able to charge the battery. On the other hand, for the discharging circuit, we designed the circuit in such a way that it will work on a range of input of 3.7 volts up to 4.2 volts. The reason for this is that the typical output values of a battery is within this range. When a battery is fully charged, it gives off an output of close to 4.2 volts, while when it's near its low battery status, it usually sends off 3.7 volts. The minimum voltage is set because the protection circuit board of the battery will prevent it from discharging past 3.7 volts to prevent damage. Upon using this circuit, it is proven that it can give an amount of approximately 5 volts while drawing 600 milliamps.
The ultimate performance of a power harvesting system based on TEC depends on the degree to which heat can be extracted by the copper coil. Using TEC, the researchers were able to present a stable output voltage of 5 volts. After conducting all the testing and simulation, could charge a 6800 mAh battery.
We also proved that the system is capable of powering a 3 watts LED bulb for 10 hours using computation. Therefore, the proponents conclude that this study is possible or feasible.
The recommendations gathered from the study are as follows. First, do more advanced research on other better available components such as thermoelectric devices, sensors, and other hardware. Second, replace the copper heating coil with copper heat pipe to enhance the conductivity of heat transfer. Third, Integrate a cooling system to further increase the temperature difference between the hot and cold side of the thermoelectric device. Fourth, utilize a computer with better specifications and performance for more accurate data and acquisitions.
Fifth, develop a booster circuit that can produce a better output. Sixth, increase the capacity of the battery used for larger storage of power. 7. Design the system wherein the user can decide where to draw power from. The source would be either from the battery when charged or from discharging circuit directly while in the act of cooking. Lastly, remodel a better chassis design with possible improved airflow and insulation.
The continuous search for a possible source of electricity is still on the move. Our goal as researchers and future engineers is towards the betterment of not only our lives, but the ones around us, especially those who are not fortunate enough to have access to this basic need.
Upon arriving in our target community, which is in Barangay Bapo Baculo, Porac, Pampanga, our team have identified the needs of our fellow marginalized countrymen and assessed the available resources to them. Their main concern is to have an adequate lighting enough to last for the night, and since they live near the mountain, wood is very much abundant to them.
Findings of our group had led us into a series of brainstorming sessions, doing researches and reading multiple research papers, articles, journals, and the like. These help us in hypothesizing our project entitled HELP, a low-cost heat-to-light thermoelectric device-based converter for houses in rural communities.
We utilize a thermoelectric device, specifically the model EEC1 12706, to be our main component in this project. This will be the main source of electricity which utilizes waste heat from cooking.
Upon the journey of our research, a global pandemic has struck, impeding us from physically creating the device, so we opted to use a simulation-based approach for this project.
Based on our analyzations from the results of the testing phase, we were successfully able to generate a feasible device that would be able to provide a 5-volt 600 mA supply for the users. This supply is expected to be enough to provide for the needs of the ICA community in Pampanga, which is to be able to provide lighting that would last for the night.